there. Like, love at first sight. He's a good boy. He's got some training he needs to do. And he's just been here and he's still really brand Yeah. That's hilarious. What is wrong with you?
Never, I mean, never hard to just drop
It's not gonna work.
I've always been jealous of these up, but I don't know.
That's scary.
Yeah, my neighbor's.
When I had my abdominal surgery, I was so afraid because I had scared cigarettes. Like, I had internal stages, but I just had serious and they had me on a walking trip. I was like terrified that I was scary.
Like after I went home, okay, he said I don't think it's crazy. Just at one point, helping. Just looked out. Hey, you're over here. And just look down, just blushing. Hey, Alma, don't freak out. See, that was why I told you not to freak out. I'm driving the house. I'm okay. I'm just saying. Holding this thing.
I'm good.
The real festival.
I'm probably gonna try to do that from now on. What? What? So it's alive, they don't fly, but they also stay up.
Because when we go to forest, it'll sink first, you get the deal up there, then.
Yes, okay, that was the dog in the house. You let the dog in. You were the time. Yeah. You got plenty of years. I cannot imagine the time.
What music was there?
Sorry.
I mean, what do I know?
No, I think that's a good.
Yeah, I like to sit around. She went on to do.
Before that, people actually didn't do now they have to tell us. I shut off from side to
And then you also did.
Someone always.
You always end up with half of that all in one direction.
You're wrong.
I mean, I guess I am, though, I'm kind of the top one thing.
Is it the saboteur?
Yes.
You should just set the bar, the Red Bull, set the bar. Right where you want it to be. Yeah. Ribs.
It's just like the right. Arbitrary. We don't. I still have it.
I have dinner actually. I have a cup of coffee.
Did that help?
Not drop.
She's very proud.
No, because I thought I had to put that too much time out of my truck. No, I put something in my truck. But then I did my cucumbers. And so,
Do not eat that.
so
So I just had like water. Now I have this. It says me too fast. So
I always go pick up a leash and a collar for Fisher today. Yeah, I did. He's in the house. I put him. I have a friend, Kate or April, gave me an extra. She had an extra large dog breed. She had like flavor protection. Oh, yeah. Okay. There. Yes. Everybody's giving me things. Great. Yeah, he's in the house. He's doing good. He's a little. It's funny. He's getting in the car. And then the car ride home, he's kind of nervous. As soon as he realized that, as soon as I put him in the car, he was stoked. He did. We went on a walk.
This is mine.
He still has not figured out to communicate the noise up. He just chases them, sniffs at them really hard, and then runs away. Oh, okay. That's great, yeah. Right, he can't run around and just we have to be to chill, and then he'll go on many adventures. I gotta get a tag made for him.
Can you hear us?
I think him stay still long enough to take pictures. I was like, we're just playing now. I'm really excited.
get like a stack of 200 stickers.
It'll be good for both of us.
Okay, so today we have Dr. Paticia Yager. She's a professor of marine science at the University of Georgia. She earned her bachelor's degree in geology from Brown University and then her master's and PhD from the University of Washington School of Oceanography. She's been at University of Georgia since 1998, and in her time there, she's been the director of the university's Climate and Society Initiative and the chief scientist on 4 large ocean research expeditions to Antarctica, the Amazon River, and the Arctic. And today she'll be telling us about how melting ice sheets impact coastal ocean productivity in the Antarctic.
Thank you. I like to walk around. Is it okay if I stand up here? Yes. We were just laughing about how my first talk that I gave, my dissertation advisor told me that I had to set down all the things that I had in my hand while I was talking because I was waving my arms too much. All right, well, thank you very much for having me and coming to my seminar today. I really appreciate your attention, and I hope I'll tell you something interesting today. I want to take you to this place. We often do science because of the things we love and why we love these things we don't always know. But this is a scene from my 2007 first trip to the Antarctic, where I really fell in love with this beautiful place. It's probably similar feeling to some of you have for the Gulf of Mexico, I would think. But I want to tell you about this place that I have been to now 3 times to understand. This is the Amundsen Sea. And it's not just me that loves this place. There are a lot of animals that live there. And for the rest of my talk, I'm not really going to talk about animals very much. I'm a microbial ecologist and a biogeochemist, so I'm afraid that most of what I do doesn't seem very exciting to people who love seals and fish and penguins. But in fact, these are the most important parts of this ecosystem from a human perspective. Oops, I'm going to trip. Of course, I'm going to tell mostly about the phytoplankton. This is the greenest place I have ever been in my entire life, and I have been to many places, including the Amazon River. So I'm going to tell you about why this place is so green. But why we care about the greenness of this place is because, of course, the food web that's here, and the krill, and there's lots of other copepods and zooplankton that I'll show you a little more about later, which is the main food for the crab-eater seal. This is the emperor penguins and the adelies. So I used to be a polar snob. I did my PhD in the Arctic, and I thought polar bears were awesome. Let me tell you, penguins are more awesome even than polar bears. They have so much character, and if you get to sit on the ice and let them come to you, there isn't any other feeling like that. Because you're not supposed to touch them or approach them, but you're allowed to sit there and let them come and approach you. Okay, and then this is a Weddell seal that I got to get up close and personal because I had a free day with some Swedish seal biologists, and I got to sample his nasal mucus and all kinds of good stuff. But the cool thing about seals in the Antarctic is they're fearless because all of their predators are in the ocean. So if you come up to a seal on the ice, they're just like, well, hello. Who are you? What are you doing here? So the seals are amazing after having seen the seals in the Arctic be completely petrified of anybody human. They're more worried about, well, I didn't put a leopard seal on here, but the orcas eat the penguins mostly. And then the Minke whales are the only whales that I saw very close up. There are lots of whales in the area, but they won't come near a moving ship. The reason we saw the Minkes was because we were parked in a section of fast ice, and they could come in and breathe in the hole that we made. So they like to feed under the ice shelf, but they can't normally breathe there. So they followed us in and then hung out in the pool of water that we made for about 3 days. So it was pretty amazing to watch these guys. And then there's different kinds of petrels who also feed on the krill and the other zooplankton in the area. So this whole system depends on this, which is what I'm going to tell you about today. And I'm mostly talking about this place here, the Amundsen Sea, which is about as far away from humanity that you can possibly get. If you don't know your Antarctic geography, that's the South Pacific going that way. And there isn't an island for thousands and thousands of miles. You can get to Chile from going to the peninsula here. And lots of boats go back and forth here. In fact, if you go on an Antarctic tour ship, you're probably likely to go this way. And then from McMurdo, New Zealand is down here somewhere. So you can get back and forth to McMurdo from New Zealand. But the Amundsen Sea has been very poorly studied over the years because it is so far away. It takes about 3 weeks, 2.5 weeks to get there from Punta Arenas, Chile. And it takes another 2.5 weeks to get to McMurdo, where you can then fly home. So the Koreans had thought at one point they were going to put a research station here because it's such an interesting place, but they decided against it because it was simply logistically impossible. So it's an interesting place. It's far away. Not too many people study it. So I'll tell you about it today. Oh, and I always start with my conclusions because sometimes I don't get to the end. So if you remember nothing else from my talk today, oops, sorry, I had a little too much Diet Coke out there in the hallway. Okay, so if you remember nothing else from my talk, I would like you to know that melting ice sheets affect more than sea level. Of course, you're sitting here at sea level, so you pay attention to the melting ice sheet reports that are telling us about sea level rise. And you should, because you will be impacted by the sea level rise. But it's not the only thing. So when you think about the sea level rise due to the melting ice sheets, I want you to also think about, oh, well, wait a minute, where's all that meltwater going? It's not just contributing to the bathtub, it's actually impacting the circulation of the ocean in these coastal systems, and it's changing the ecosystem and their response. And then on top of that is that ice sheets aren't the only thing that's changing, and you all know this too. Lots of other things are changing with climate change as well. So I will end, hopefully, if I get there, by telling you a little bit about what we think the future of these systems looks like. Okay, so I always start with this one, because this is the root of all evil. Increasing CO2 in the atmosphere over the last, well, this is the only, 60 years. When I was a grad student, we were quite freaked out about the fact that it was 350. Now it's 400. So we're, and the rate of increase is going up every year. We know that the CO2 pre-industrial was about 280 from the ice shelves. So we've almost increased by more than 50% the CO2 in the atmosphere since the industrial age. And the doubled CO2 scenario that we've all sort of hypothetically discussed over the years is about to happen in mid-century. So where's this carbon going? Most of it, a big chunk of it is, let's see if I can do this. Okay, as of the latest, this is LeCarre 2018, we're putting almost 10, and these are gigatons per year, into the atmosphere from our fossil fuel burning. Another one or so, maybe 2, from land use changes, and about half of it is staying in the atmosphere. A third is going into land, greening of the terrestrial system, and then about a third, maybe less. This number is not changing, and these numbers are all increasing. So we don't know very much about changes in the ocean sink. Most of the ocean sink calculations are based on very long-term studies. But about a quarter to a third is going into the ocean. There's a little bit of an imbalance that I personally think is probably going into the perturbed ocean, but we don't have any data for that yet. So the ocean's been doing us a favor, and I guess you've been hearing a lot about ocean acidification. So you know that the ocean has been doing us a favor, but also suffering from the consequences of taking up that extra CO2 for us. It goes into the ocean by these 2 mechanisms. Hopefully I'm not teaching you anything new. This is the biological pump and the solubility pump. The solubility pump is the cold polar water taking up CO2 in high concentrations, also oxygen. And then when that deep water sinks, it takes the high CO2 down to the bottom. And the biological pump is, of course, the photosynthesis dominating over respiration, and some fraction of that new production goes down into the deep ocean, sinking where it's respired at depth. So we have an ocean. If you don't know much about the carbonate system, the CO2 in the surface ocean is very much lower than it is in the deep ocean, which is great because that means that the atmosphere will be lower thanks to these pumps. So the way I like to talk about this, and I will get to the Antarctic in a minute, I promise, I'm giving you my bigger picture, why do I do what I do? Because someone asked me this morning, why are you doing both Amazon and Antarctic work? So this is why. If you turned off both of these pumps, so let's kill off everything in the ocean and take a giant egg beater, stir it all up. So that CO2 gradient, that high CO2 bottom water is now mixed completely through the entire ocean. And this was just a little mass balance box model study done in the 90s. If you turn off both pumps, CO2 in the atmosphere would be 720 ppm. I just showed you it's 400 right now, and that's kind of higher than it used to be. So 720 compared to the 280 pre-industrial. So those pumps are really keeping our climate much milder than it would be if the ocean was well mixed and dead. So those things are important. If you just turn on the solubility pump, keep the biological pump off, so you just have deep water formation at the poles, you can get the CO2 in the atmosphere down to about 500, depending on how you set up the deep water pump, but you can't get to 280. So this gives you a sense of the importance of the biological pump. Turning on the life in the ocean brings the CO2 in the atmosphere down to 280, which is the pre-industrial value. But you don't even have to turn it on full way. We call it partially turned on, because what you're doing is leaving some nutrients at the surface that you don't have to use to get the CO2 down to 280. If you want to do a full biological pump, all the potential of the biological pump turned on, you can get down to 165, which is as it happens what it is during an ice age. So what we knew from the studies of the ice age mechanism is the trigger is the solar cycle. Maybe you've heard about Milankovitch cycles and the Earth going around the sun. But we knew that the heat budget from that rotational change is not enough to cause an ice age. You need an amplifier. And that amplifier is the CO2 in the atmosphere. And it seems that it would be possible that amplifier is driven by a biological pump. So that was 1991 when I was a brand new shiny graduate student. And I thought that was amazing because if a biological pump can do this, maybe it can do this. So the optimism was that maybe as climate changes, the biological pump can respond and maybe help us out with this problem. Of course, the opposite is also possible, right? That the biological pump might shut down under climate change and make the problem that we have much worse. So that's the motivation for what I do. How do you make a more efficient biological pump? As I mentioned, you use the unused fertilizer at the surface. So the nitrate, that's here in the North Pacific, these high nutrient, low chlorophyll zones, where they're leaving behind potential, which is nitrate in the surface. And of course, if you look at this figure, you immediately say, well, we should be looking at the Southern Ocean, right, for this potential. What's driving productivity in the Southern Ocean? How can we turn the biological on? And perhaps you've heard, if you've been around long enough, some of these iron fertilization proposals. Give me a tanker of iron and I'll give you another ice age. Talks about fertilizing the Southern Ocean. Well, it turns out we don't have to use tankers. We may be doing it indirectly through melting ice sheets. So whenever I talk about systems in the ocean that it's possible that they're going to change in response to climate, I have to remember the words of Smith and Mackenzie, which is, in order to talk about an anthropogenic CO2 sink, it has to be a perturbation. It can't just be something that's been happening anyway and this nice big carbon sink. It has to actually be a perturbation. So anytime you're looking at a CO2 change, or a CO2 sink for anthropogenic carbon, it has to be different from what it was before. And it also has to be big enough to matter. If I find suddenly that there's a new CO2 sink in my backyard, that's great, but it's probably not going to help out the planet. So I have spent the last 20 years or so wandering around the world, a lot in the Arctic, off of Barrow and the Chukchi Sea, in the North Water Bulimia, here in the Labrador Sea, and in the Northeast Water Bulimia, places where CO2 is going into the Arctic Ocean, increasingly so because climate is changing there. I've also worked a fair amount in the Amazon River plume. Amazon River is, Amazon River is the largest river in the world, of course, and its plume reaches almost all the way across to Africa during parts of the year and up to the Caribbean during other parts of the year. It has a huge influence on the carbon budget of the equator, of the tropical Atlantic, enough so that it actually flips the direction of carbon flux in the tropics. The CO2 flux of the equatorial region is mostly out of the ocean, and if the plume flows over this region, it reverses it and causes CO2 to go into the ocean. So it's a really, and of course, it's a very climate sensitive. I used to think it's hot. Making it a little hotter is not going to matter too much. So why do we care about climate change in the tropics? Well, guess what? Water cycle, warm tropics. The hydrologic cycle of the tropics is on steroids. It's amplified. They have more floods and more droughts in Amazonia these days than they have ever had. We used to argue about whether it was going to get wetter or drier in the Amazon with climate change. It's doing both. They're having more extreme events on both sides. Okay, so now that gets me down to the Amundsen Sea, which I'm going to tell you about today. So the big question was, why is the Amundsen Sea Bulimia taking up? Well, Bulimia means open water surrounded by sea ice. It means pool in Russian. Why is the Amundsen Sea Bulimia taking up so much CO2 from the atmosphere? And is this sink climate sensitive? That was the main research question. Before I go too far, I have to tell you a little bit about the jargon of ice in the Antarctic. Mostly the big difference is between the land ice, that is like what you think of when you think of a glacier. It's ice that comes down from snow and gets compacted and makes a glacier, or in this case, an ice stream. The whole continent is a giant glacier, or an ice sheet. As the ice stream works its way down to the ocean, there may be an ice rise here. This is called the grounding line. It's the last place that the glacier feels on the bottom before it starts to get ocean underneath. This is called the cavity. Maybe or maybe not, there's an ice rise supporting it, and there's another cavity here. Icebergs are what big chunks of ice melting off of the ice sheet or the glaciers. They're usually hundreds of meters tall or thick. They calve off. And then the katabatic winds are the winds that are coming off the continent, pushing towards the ocean as the air cools. All right, and then there's the sea ice on the other side. Sea ice is actually frozen ocean. When the air temperatures get really low, ocean temperatures will drop to about 1.8, minus 1.8 or minus 2 degrees centigrade. And then the ice crystals will start to freeze, and you get, in fact, you saw on that first photo I showed you what's called frazzle ice, which is the little organizing ice crystals, and then they solidify, and the salts get extruded. So you can actually melt sea ice and drink it. It has a salinity of about 4. a little bit salty, depending on how old it is. But anyway, it's mostly fresh water that's frozen into ice, and then it floats on top of the ocean. So lots of sea ice out here in the frozen ocean, and then this area in between, the open water, mostly driven initially by the winds. The winds push the sea ice offshore, pile it up offshore, and there's an opening here between the ice shelf and the sea ice called the Bulimia. And there are winter Bulimias that are very, very important for Deepwater formation because you have really, really cold air and the ocean open to the air, and then that water sinks very fast. Summer Bulimias are initiated by winds pushing the ice offshore, but as soon as in the summertime when the sun is shining, the ice is a high albedo or reflecting surface, and as soon as a little bit of ice melts, you now have dark ocean. So the ocean starts to absorb the heat and warm up, which melts a little more sea ice, and then warm up a little more and melts a little more sea ice. So in the summertime, the Bulimias expand due to the sunlight and not just the wind. Okay. So the Amundsen Sea embayment is famous across different disciplines, mostly because of its melting glaciers. This is the, well here, Pine Island Glacier, the Thwaites Glacier, the Haynes, the Pope, the Smith, and the Kohler. And then each of these has an ice shelf coming down to meet the ocean. Pine Island was in the news quite a bit in the last few years because it was melting very, very fast. Thwaites is now in the news because it's a much, much larger ice mass that could contribute, if it collapses, about 3 meters of sea level all by itself. So there's a big US-UK initiative called the Thwaites Invasion. Actually, I think that's an informal term. Driven by UK, of course, talking about invasions, but it's the British Antarctic Survey and a bunch of NSF folks working on the Thwaites because of its potential to really raise sea level. And you can see from these figures that these glaciers are, this is the change in flow speed or the acceleration over the last 15 years or so. Really rapid melting going on here. And just to give you some perspective, this is the Pine Island and the Thwaites over the years in gigatons water per year. A gigaton is 1 billion metric tons. So they're the two fastest melting ones. The others are melting a little bit slower. And if you add them all up, just the Amundsen Sea embayment, it's about 350 gigatons of ice per year coming off. 360 gigatons is about 1 millimeter if they're distributed over the planet. So currently sea level rise is about 3 millimeters per year or so. So just alone, this part of Antarctica is contributing about 1/3 to sea level rise. And if you don't think in gigatons, not too many people do, I can convert it to elephants for you. A male African elephant weighs about 6.8 metric tons. So a gigaton is well over 100 million African elephants. So 350 gigatons, which is what we're losing up here, is about 50 billion elephants. That's a lot of water every year coming off of this glacier. So we got a lot of problems here, a lot of water. Why is this place melting so fast? Eric Steig at the University of Washington did the surface heat budget and noticed, first of all, that Antarctica, West Antarctica is warming up quite a bit. But when he did the math, he found out that the air temperature was not enough to explain the really rapid ice losses in this part of the continent. So oceanographers started wondering, what are the other sources of heat? And what they realized very quickly was that the Antarctic Circumpolar current, which is about the temperature of your refrigerator, about 2 degrees centigrade, that the Antarctic Circumpolar current comes up closest to the Antarctic continental shelf here in the Amundsen Sea embayment. So it's bringing that warm water in very close proximity to the places that are melting the fastest. So that was our first clue that something might be going on in the ocean. And this was all happening about 2010. And what they came up with, this is Doug Martinson, is that this warm, by warm I mean 2 degrees, circumpolar deep water is flowing up. Did you know that the continental shelf of Antarctica tilts towards the land? Unlike your continental shelf, which tilts away from the land, the continental shelf of Antarctica tilts towards Antarctica. And that's because of the weight of the ice sheet, right? So that means that any warm water that makes it over this sill can go cascading down into the bottom of the ice. So it's about 1,000 meters deep here. There's trough systems, of course, but about 1,000 meters deep here, and it's about 350 meters deep out here. So if that water, that dense, salty, circumpolar deep water can break through and get over that shelf, it rolls right down like a waterfall into the bottom of the trough towards the ice shelf. And of course, it's warmer than the ice. If you put ice cubes in your refrigerator, they do eventually melt. And so it's melting the ice sheet from underneath and causing it to collapse. It would be just like removing the toe of a landslide and having it keep slipping as you kept removing the toe. Okay, so I've convinced you hopefully that we've got melt going on here. In this same vicinity are two really important coastal polynyas, the Pine Island polynya and the Amundsen Sea polynya. Both of them are known to be very highly productive. You can see them on satellite. They're some of the greenest areas in all of Antarctica. Greener than the Ross Sea, greener than a lot of the other small polynyas in this area. I'm going to tell you the Dodson ice shelf is sitting right here between the Kohler and the Smith glaciers. I'm going to be talking to you about the Dodson ice shelf because it is the one that abuts right up against the Amundsen Sea polynya. The Pine Island abuts right here. So a lot of the things that I say about the Dodson will also apply to Pine Island. So what about this polynya? What did we know before I was invited to go on the first cruise of opportunity to this region? From Kevin Arrigo's satellite work, we know this is primary production over the annual cycle. Of course, summer is in the middle of winter for us. November, December is the peak in productivity. And this is the line for the Southern Ocean. Southern Ocean's not very productive. I mean, it is relatively speaking, I guess, compared to other parts of the ocean, but compared to other parts of the Antarctic, it's not very productive. Here's the average of all the polynyas. And then the red is the Amundsen Sea, has the highest mean productivity of all the polynyas and the highest interannual variability, which is kind of interesting. Usually as a climate change person, I think about interannual variability as a really good sign that there's a climate driver. Because climate, of course, well, there's a mean climate, but then there's interannual variability. So the highest primary productivity and the greatest interannual variability in a place, oh, I haven't mentioned the sea ice yet, hang on. Ice sheet, fourth largest polynya, always there. Okay, and then the final piece is actually what we were going to focus on, which is Sharon Stammerjohn's looking at the sea ice in this region. She's mostly worked in the peninsula area to show that the sea ice in this is the Bellingshausen Sea in the Western Arctic Peninsula, has been disappearing. And if you follow any of the Palmer LTER work, you'll know that the changes in the sea ice in the Palmer LTER station have dramatically changed that ecosystem here off of the Western Arctic Peninsula. So these blue areas on this map are places where the ice season, so sea ice duration, how many days of the year, how many months of the year are you covered up with ice versus open water? So in these blue areas, the rate of change, and this is from 1970 to oops, I lost my, I think it's a 20 or 30 year change. How many days over that 20 or 30 years per year? So this is a 4 or 5, 6 degrees fewer days per year over 20 years. So we're talking about 2 or 3 months of more open water in some of these areas than they used to have less than 40 years ago. And on the edges is the Amundsen Sea polynya. The Amundsen Sea polynya is part of this trend where there are more open water days now than there used to be, and the polynya is opening up earlier than it used to, and staying open later than it normally would. So we've got sea ice change, we've got glacial melt, we've got all these interesting things. So we piled together a whole lot of people and went out on the international. So we got to use international. This is my favorite acronym of all time, ASPIRE, Amundsen Sea polynya International Research Expedition. And you can read about, oops, there was a really early article I wrote in the Oceanography Journal that's very accessible, I think, if you want to read more about the story And then the 2016 summary that I put together in Elementa is also open access. You can look at that if you're interested. But lots of really amazing, talented postdocs, the Polar Trek teacher, some really great US and international PIs, maybe you recognize some of them, went on the Palmer, and we had about 25 days in the Bulimia. And this is what our cruise track looked like, just so you know that I'm crazy. So we would do science stations, because all the biologists, they just need like a few liters of water, and they're happy for 24 hours. Sharon and I would drive the boat. I didn't point out Sharon. This is Sharon up here. Sharon was the physical oceanographer and the sea ice person. So she and I would be, okay, where are we going to go? So at night, while everybody was working, we would just drive around and try to get synoptic coverage of the area. And you can see that the chlorophyll is crazy high here in the middle. It's about 30 micrograms per liter. In the middle of the Bulimia, it goes to zero very quickly as soon as you get into the sea ice. And also zero here next to the Dodson ice shelf. Quite an interesting place. And this was work done by the group at Rutgers who has these beautiful gliders. Oscar Schofield stuck out a glider, so we had even more coverage than the ship. And his data show this really nice trend. You know, salty, cold winter water has very little chlorophyll in it. But as you get fresher and warmer, so that's basically the marginal ice zone, and then the Bulimia is where the chlorophyll builds up. So you need that really nice stratification provided by the sea ice melt to get the bloom. It just doesn't pop up anywhere. You have to, you know, noticing that there's no chlorophyll here by the ice shelf or here, you really have to get out into the open water that's got this really nice shallow mixed layer to get the bloom. And you don't get bloom in the sea ice itself. And that's just makes sense, right? The nutrients are coming from below and the light's coming from above, and there's this sort of sweet spot for the phytoplankton. And marginal ice zones, if you don't know, you can go to the Arctic, you can go to the Antarctic. They're famously productive places because of that nice shallow mixed layer. So what was blooming? This crazy green place, the most greenest water I've ever seen. Well, it's also really stinky. Have you ever smelled DMSP? Or DMS, it's just DMS, sorry, I always say that wrong. Phaeocystis antarctica is a promesiophyte algae, usually, well, sometimes solitary, but we found it in crazy colonies everywhere. Gooey, gelatinous matrix of colonial phytoplankton. It lives in the sea ice and then is sort of seeded into the seawater in the spring. It can survive long dark periods. It's quite a talented organism. Like I said, it makes a lot of DMSP, which then turns into DMS. Back in the days when I still had my smell, you brushing your teeth in the water that the ship has made from the seawater is nauseating because it's got so much of that sulfur smell in it. And the other interesting thing about it is it has a fairly low iron requirement, which will become important in a minute. Okay, so what happens here? So these same places where the chlorophyll is high, the CO2 is crazy low. We got CO2 drawdown as low as I've ever seen it, down to about 100 parts per million. Again, remember the atmosphere is 400. So the net photosynthesis relative to respiration is very high. Lots of carbon being drawn down and sucked into these organisms. My master's student, Lynn Mew, looked at the oxygen saturation versus the PCO2 saturation. This is a nice way to look at data if you have data like this. If you're super saturated in PCO2, you either have a lot of respiration or you have warm water. But if the oxygen is also super saturated, that would be, this is the zone. If you have data up here, sorry that map is in the way, but data that were up here have super saturated of both gases, that's just warming. Data that are super saturated in CO2 but undersaturated in oxygen is respiration, right? And similarly up here, super saturated in oxygen but undersaturated in PCO2, that's net photosynthesis. So this plot kind of lets you look to see what's happening across all of that underway data. This is all surface data, the black dots. We can see some areas in the winter water are starting out with net respiration. Winter water, you have respiration dominating over photosynthesis. Most of these data are near the ice shelf or in the sea ice. And then as you go up, you move into the zone where you have lots of photosynthesis, and you can see the oxygen increasing and CO2 decreasing. And there is a little bit of a signal. If you just do a photosynthetic quotient, you get on the green line. If you do photosynthetic quotient plus a little bit of warming, which we saw, surface warming, of course, you get on the blue line. So we can see that this is happening is because of what we think is happening, which is the phytoplankton bloom. Okay, if you do the calculation of the CO2 flux, how much CO2 is going in? It's big. We're talking, well, the rates are higher than anywhere else except the one place I've also been, which is the Chukchi Sea, which is also a crazy productive part of the Arctic. It's 50% larger than the Ross Sea, which is a well-studied pulling on the other side. If you like to sum up things and see, okay, well, what's the total amount of carbon going into this Bulimia? It's about a teragram carbon per year, so that's a lot of carbon. Interestingly, that's 2 to 3% of the calculated uptake by the entire Southern Ocean in about 0.25% of the Southern Ocean area. So if you think about that, that means that this little patch is taking out CO2 10 times faster on average than the rest of the Southern Ocean. We also looked at, how am I doing on time? We also looked at the fate of this carbon. I did a huge carbon budget. This is the 2016 paper. It was like my albatross for many years trying to finish this thing. I tried to look at all the pools of carbon and all the flows and calculate the budget and figure out export to make sure that whatever was coming in here was also going out here, because you don't get sequestration just in the surface water. You have to get it down. So we did a lot of work, not just me, lots of people doing all this budgeting. And just to quickly go through this, I want to show you, you can look at the nitrate profile. So if you're used to looking at nutrients, the nitrogen, the dissolved inorganic nitrogen in this system is about 33 micromolar in the winter water. It's lots of nitrogen. But we can go to stations like this one here in the middle of the Plume where the surface profile goes down to about 7. We didn't see it any lower than a 7, so we don't think that the system is nitrate limited ever. But it is able to draw down from 33 to 7. And you can integrate the missing nitrogen from the winter water and calculate a net community production. And if you do that for all these stations that we visited, you get a gradient. We have some stations that didn't have much drawdown at all. We'll call those early bloom. The net production was fairly small. The middle zones here on the edges, down here, I'll call mid-bloom, and then peak bloom here in the middle is where the nitrogen was drawn down the most. And I'm calling that high bloom because we had to leave before the peak bloom was actually happening according to the satellite. So this is the net community production. It's the drawdown of nitrate and turning into organic matter. And it happens along a really nice gradient. So of course this is crazy matrix, spatially heterogeneous, patchy place. But it turns out I can organize these stations according to the drawdown into kind of a temporal sequence, if you'll let me do that. And believe me that I can look at each one of these stations and sort of put them on a timeline. The nice thing about it is that the timeline corresponds directly with open water duration. So you can see from the satellite at every one of these stations how much open water that station has experienced. And we call that open water duration, and it's a nice linear relationship with this drawdown. So it's very, very tightly coupled to the solar input. And as the DIN gets drawn down, this is that same gradient, that same bloom progression going from left to right for the inorganic carbon drawdown and the inorganic nitrogen drawdown, while you have a buildup of particulate organic carbon and particulate organic nitrogen. And the Redfield ratios are right on. It's pretty amazing. Here's the biomass buildup, the chlorophyll buildup. This is just the upper 100 meters or so. We had a fair amount of bacterial biomass, nanoflagellates and dinoflagellates, ciliates, hardly any macrozooplankton in the surface waters. I'll show you in a minute. They're all below 100 meters. But we did have some significant microzooplankton going on. Here's the copepods. Like I said, they're all hanging out. This is kind of blurry, sorry. The green is the mixed layer and the chlorophyll layer, and these are the peaks in the zooplankton hanging out below the bloom. They don't like swimming around in this stuff. That green soup is too dense or too soupy, and it's not a place they like to live. So they're probably feeding on the sinking flux as it falls, and there's no migration. I didn't put the nighttime, daytime profiles on here, but there is no diurnal migration at all. Okay, so I can do the big budget. I'll save you the details. Basically what I found is that all of the drawdown here, some fraction of it is being exported. Some of it is still hanging out in the water column. These are two stations where we had sediment traps, and I can compare what I think is sinking to what we captured in the sediment trap, and it matches pretty good. And the 360 meter trap, a long-term sediment trap that Hugh Ducklow put out, captured an annual flux, and it all matches pretty good with an export of about 3 or 4% of the surface productivity. So that's a pretty good efficient system. So how do you get all this drawdown of nitrate, all this carbon flux in a place like the Southern Ocean, which normally should be nitrate limited? High nutrient, low chlorophyll. Well, you probably already guessed, the answer is iron. So for the last part of the talk, how am I doing on time? I didn't bring my clock. 10 minutes? Oh my goodness. All right, well, 10 minutes, I'm going to share with you how we get iron into this Bulimia. And you might have already guessed it has something to do with the melting ice shelves. But it's not what we thought. So we first thought it's just the glacial melt coming off of the ice shelves. Well, it's a little more interesting than that. And I'll show you that data. Oh, the other thing I wanted to show you is if you're interested in genes, and I know, Paul, you're interested in this stuff, we looked at the genes, and the Phaeocystus seem to have some friends that are living in the colonies, helping them collect iron and cobalamin, and they're feeding them fatty acids and DMSP. There's some really nice papers by Tom Delmont looking at the genetic signature from these blooms. Okay, so this is called the iron curtain transect. This is the Dodson ice shelf. Oh, and I usually try to put 2 local places on here. It's about 30 miles, Athens to Winder, but that's nothing to you guys, sorry. So what's a good 30-mile range here? It's bigger than it looks, I guess. It looks so small because the air is so dry and clear, but it's about a 30-mile trek across from here to here. So we had a cowboy for a captain who let us sail the ship way too close. We saw one avalanche that we got kind of scared about, but we were not deterred. We kept going, and we measured CTD all along the edge and ADCP and all those kinds of things. This is, I can't really take credit for this. This was Rob and Sharon's brilliant idea. I have to give them full credit for doing this. So here's just some data to show you what we found. Again, going from this end to this end is going from here to here. This is we had that multi-beam close enough that we could, oops, uh-oh, what did I do? Okay, there it is. Okay, here we go. Left to right, this is the ice shelf draft that we got from the multi-beam. It's about 100 meters-ish thick, plus these sort of zigzaggy things reaching down. So this is 0, 200, 400, 600, 800. Here's the really deep trough in the middle. That's about 1,200 meters. So that's the seafloor. We also got off the multi-beam. ADCP doesn't get all the way to the bottom because of the frequency, but so the blue is going, let's see, so at this end, the water is coming out here. So red is coming out here, and blue is going into the file. So here was, do you think in spherodrips? You don't think in spherodrips? Probably not. Okay, 0.16 spherodrips is an Amazon River. So my 2 worlds collided. I've got an Amazon River coming out from under the ice shelf. Now, it's not pure fresh water. When I say Amazon River, I'm just referring to the flow. The meltwater fraction of this layer coming out from under the ice shelf is about 1.5% meltwater. But it's crazy high in particulate iron, and it's crazy high in dissolved iron. So a very nice outflow coming out from under the Dodson of iron and meltwater. So, but we didn't know what happens to this current. So I was very fortunate to stumble across two really amazing collaborators from Old Dominion. Pierre Saint Laurent in particular was a young postdoc when I first met him. He's now a research scientist at Old Dominion. And he had a ROMS model, Regional Ocean Modeling System model, which Old Dominion is sort of famously for expert at. Mike has one for the entire continent. It goes around the whole continent. It's amazing. If you ever get a chance to see him at a meeting, just watch his movies. So Pierre was showing these movies of these beautiful eddies of meltwater just flowing. Here's the Dodson right here, here. All these eddies of meltwater coming off, and I'm like, that's how the iron is getting to my phytoplankton. So we wrote a proposal and got funded to use a model to sort of test to see how this all worked. And we've got a couple of papers out this year. This is the model showing you the circumpolar deep water that I mentioned in that one cartoon coming up onto the shelf. So this is the ACC out here in red. Here's the Dodson ice shelf right here. This is the Getz ice shelf. Here's Pine Island. This is a big iceberg. And then the white is the Bulimia area. So this is deep water, bottom water concentration of circumpolar deep water. You can see that it's come all the way up underneath the Pine Island and underneath the Dodson through these trough systems. Okay, so then here's the meltwater fraction, the tracer for the meltwater, showing how the meltwater is now coming off the ice shelf and going into the Bulimia. So this is the one that was similar to the model I saw him generating, these lovely little filaments of meltwater moving into the Bulimia. But here, and I actually wish I could speed this up a little bit, this is the circumpolar deep water tracer at 100 meters. And it's going to be kind of slow. Here it's starting to appear. So circumpolar deep water is supposed to be deep water, right? It's not supposed to be at 150 meters. But here it is, coming out also with the same path as the meltwater. So what that meltwater did was it melted, the circumpolar deep water melted the ice at the base of the ice sheet at 650 meters. And then that meltwater made the circumpolar deep water buoyant. So we're not only bringing meltwater to the surface, we are bringing deep water to the surface. And you all know what deep water does when it upwells to the surface. It brings nutrients with it, right? So it's not wind-driven upwelling, it's buoyancy-driven upwelling from the meltwater injected at 650 meters depth. So if you plug, here's a little cartoon. We did one of those, you probably get emails about this all the time, research features. We will do an article about your research and put it in a nice magazine that's got beautiful color photos. Well, okay, they did. It cost them $1,500, but they did make us a nice graphic, which I couldn't have done myself, so it was worth it. So here's the circumpolar deep water coming in. Here's the other one piece of information that's interesting if you're a benthic person, is that the circumpolar deep water that's out in the ACC has a certain amount of iron in it. By the time it gets to the base of the ice shelf over here, it's got more iron in it. So we know that it's also picking up iron as it moves along the shelf. So there's continental shelf. So there's iron and resuspended sediments that are getting into that water and adding to it. So then it comes and it gets to the ice, the basal ice, melts it, works its way through the cavity, and then comes out as part of a coastal current that's also bringing water from the Thwaites and the Pig from upstream. And then that's where it's exiting, where we measured it exiting, contributing to, in eddy form, to the productivity of the Plume. We also know that the icebergs themselves are doing some interesting things. We happened to encounter one on one of our stations. We were looking at the CTD profile going, that's a really strange looking profile. And then someone said, hey, look out the window. There's a giant iceberg right off where we were sampling. So they're like a big stir bar reaching down, stirring up the iron from below as well. Okay, so that's the summary story for that. I think I'll skip this part. We we've done the experiments. Pierre's paper is published last year. The iron in the surface, you can't match it to the observations without the circumpolar Deepwater and the sediment iron that's brought up through this meltwater pump mechanism. Okay, so then in theory, we can just say, well, how much meltwater is coming out? How much of this pump is happening? That's how much productivity there is. Unfortunately, the meltwater flux over time has been calculated by some physical oceanographers, and it doesn't match very well our satellite productivity. And of course you know this, because it's not just one thing that controls phytoplankton. They need light, they need mixed layers. So this is Hilda. If you encounter Hilda Oliver at a meeting, introduce yourself. She's an amazing doctoral student. She's defending probably this April, so if you know of any good postdocs. She's been running a biogeochemical model, nitrogen, sort of an NPC type model, but we added a big iron piece to try to understand how does this delivery of iron from this mechanism translate into primary productivity. And it depends, of course, on light. And in fact, light is the limiting factor for a large part of the spring bloom. And it's only once they've started self-shading, so that crazy green water, they're not doing themselves any favors because they're totally shading themselves. And they become light limited as soon as the biomass gets up too high. And then once the biomass is light limited, they slowly draw down the iron to a point where the iron becomes limiting. So we think that the iron light co-limitation is caused for the end of the bloom. So she's working on this mechanism. Oh, and then we dropped her 1D model. Let's see if this will go. Nope. Oh, rats. How do I get the model to start? Oh, there it goes. Oh, I can do this. That's right. Sorry, I'm not very graceful. There it goes. Okay, so the 1D model that Hilda built has now been dropped into Pierre's 3D model, so we can get an annual cycle of the Bulimia, and this is the sea ice drawing away, opening up in the Bulimia. At the same time, you can watch the nitrate, get drawn down, the algae build up, and the iron goes to zero in the Bulimia. So we can now look at this in 3D with this biological model and play around with it, and actually the ultimate goal is to start playing around with boundary conditions and see what happens when we change the meltwater. Okay, I'm running out of time. Just one last word that's kind of interesting before I finish. So since I published my paper looking at that export flux, my Korean colleagues have published a paper that says, nope, sorry, our sediment trap didn't capture any downward flux. All of the carbon is exiting out of the Bulimia back into the atmosphere. And that's based on their sediment trap data, which is from this part of the Bulimia. So Pierre actually was following the particle production and the particle flux in our 3D model. And what's really cool is that all the particles are sticking to the coastal current that you might have seen in his movies. All the particle flux is going out towards the Ross Sea over here, where nobody put a sediment trap. None of us thought to put a sediment trap here, so we totally missed it. So this is where using these models has really illuminated what we need to do next. The next time we go down there by ship is to try to put things where we think that they're actually happening. Nice work. Oh, what does the future look like? So Hilda ran her model with the sea ice. So the issue is that the sea ice is still melting away. What happens to the system when the sea ice starts to go away? We just bumped it back 2 weeks earlier, which is the scenario probably for about 10 years from now. If you bump the sea ice melt a little bit earlier in the year, there is still enough light that you still get algal biomass bloom, you get a nice primary productivity, and actually ultimately you get a little bit more carbon export. So here's the perturbation response that I was looking for. We're getting more carbon out of the system under a climate change scenario. The problem with this, and she's running this right now, I'll probably have it for AGU, is what happens if you push the sea ice melt really early. Too early for the sun to be doing much for the phytoplankton. Will this actually shut down? How early does it have to melt before that marginal ice zone effect of the nice shallow stratification kicks in? So we're still working on the doomsday scenario. What happens with the total loss of sea ice? What I'm worried about is that that the carbon flux that we see today, which is mostly intake, a little bit of outtake here where the upwelling is, that's going to go away if we lose the productivity, because that upwelling, buoyancy-driven upwelling, is bringing really high CO2 water to the surface. And so we might lose our carbon sink. We might actually have a carbon source. This is not completely out of the realm of possibility. This is the Northeast Water Bulimia, where I did my PhD 20 years ago, 23 years ago. Okay, this is what it looked like back in the 80s. It was a reoccurring open water Bulimia off the northeast corner of Greenland. This is what it looked like the year we went. A nice, beautiful Bulimia, like I showed before. This is the polar bear I got to see on my 30th birthday. If you go and look at ice maps of this area recently, it's completely gone. There is no Bulimia there anymore. All it is flowing sea ice out of the Arctic. So there's no marginal ice zone, there's no productivity, there's nothing going on here. The oasis is gone. So it's not out of the realm of possibility that this could happen to the Amundsen. So I will end there. Thank you very much. I will tell you again, if you remember nothing else, melting ice sheets impact more than sea level. Thank you.
I'm curious what tracers you guys were using for your models to trace those water fluxes.
Well, Pierre just makes passive tracers that are just little parcels of water that move with the ROMs. It's just a parcel of ROM. ROM's model lets you drop a parcel in and follow it. That's the nice thing about ROMs, is it lets you follow it. And he would drop a parcel, he would drop an iron parcel different places and just follow where it was passive tracers. The 2017 paper was just passive tracers to see where the iron was going. The new paper will be now, okay, let those tracers be active and biology can draw them down and what does it look like. So that last movie I showed was the actual, let the biology take away the iron, not just deliver it. Does that help? Yeah, it's just the ROMs, it's just following a parcel of water. And then once you drop the iron into the model, I'm not explaining it very well. I'll show you the paper. I'll send you the paper. Other questions? I could try again on that one. I think it's called the passive tracer. It's just the way the model follows the parcel of water as it moves.
The ROMS has a great particle tracker.
Yeah, it's in the, yeah, that's
so
one of the
Rangian particle tracker, it's great to follow anything around.
Yeah. Yes.
DMS, you said there's a lot of DMS they produce.
Yeah, you can
Is that
smell
involved
it.
in cloud production? Am I making that up?
No, you're right about that. Yeah, so when DMS goes into the atmosphere, it's a cloud nucleating chemical, and so yeah, it's actually pretty tough to get good satellite images from this area because it is kind of cloudy.
Are there any consequences of that here that you think? I don't know. I'm curious about what your thoughts are on that.
Well, again, it could be a self-limiting thing where if the phytoplankton are really abundant and they're making a ton of DMS, they might cloud themselves out and shut down their light also, in addition to self-shading. Yeah. So if it gets cloudy, then their light availability would go down. And we think that's happening lots of places where you get phytoplankton blooms. Anywhere you get that sort of coastal marine haze, when there's a phytoplankton bloom offshore, you get that funny smell in the clouds. Yeah.
Thanks.
Mm-hmm.
So we're not going to grocery today because of our inclement weather. We're going to go down to Woody's. So if you want to join us for a beer at Woody's, come on down. We'll be there as soon as we can get out of here.
Thank you very much. questions from the other audiences, or can they ask questions, the other remote campuses? Do any of the remote campuses have questions? Sometimes I forget. No? Well, tell them, you can email me. Thanks again.
Yeah, most of their mics. Nobody was in the room. The mic was somebody. Nobody goes to that. Just gonna get you down back with yes.
I was gonna say,
As long as you come up
that's great, where were you?
Oh, I was in the Navy. So once I'm nice right there, so we just. Thank you, sir.
A naval.
It was at,
as long as you coordinate.
which was,
I'll do it.
the Russian land-based program. Coast Guard.
Whoever gets
It's
it
gone.
first,
Yeah,
Laura,
Polar Sea and the
thank you.
Polar Star are still, well, Polar Star